To solve a second order equation like this that involves these unit step functions, we're going to use Laplace transforms and use what we've just learned in the last couple of videos to take advantage of that. So before we do, let me note that the right-hand side here is the difference of two step functions, so we could also write that as a pulse function, in this case from 2 to 4. And you can look back in the notes earlier to see where we have that. So we have this differential equation, and let's have some initial conditions. Again, if we're going to do Laplace transforms, it's convenient if we're given initial conditions, so we don't have to deal with arbitrary constants. So as always, we're going to start by taking the Laplace transform of everything and moving relatively quickly through this because we've done ones like it before. The left-hand side, the second derivative, becomes s squared times y, capital Y, minus s times the initial value of little y minus the initial value of the derivative of little y. Then the Laplace transform of y becomes just capital Y. And then on the right-hand side, if you look back, the Laplace transform of the pulse function is from a to b is e to the negative as minus e to the negative bs all over s. Again, just the difference of those two unit step functions. So once we plug in the initial conditions, we have s squared times y minus s times 1 minus 0 plus y. And then, as always, our goal is to solve for capital Y, and then we'll take the inverse Laplace transform after, of course, doing some algebra, as always. So moving things around here, we have s or y times s squared plus 1 minus s. And then after a little bit of shifting around, if we add the s to both sides, and again, as we've done before, we want to get one fraction on the right-hand side. So we have all this plus s, and since we want to have one fraction, we would have s squared over s. So we would multiply that s on the right side by s over s, so we can combine into one fraction. And then we would divide by s squared plus 1, and that gives us y. So y equals this. As always, to break this down, we need to do some partial fraction decomposition. Now, let me warn you, this partial fraction decomposition problem is going to look a little different, and the main reason for that is these exponential functions, which are actually going to show up in our constants, quote unquote, the a and b and so on. So it's a little quirky, but follow it carefully and you should be okay. To do this, as always, we're going to factor that denominator. Of course, it can't be factored any further. S squared plus 1 doesn't break down any further. So what that means is, if we start our partial fraction problem, we have all of this over s times s squared plus 1. So that means that we're going to have one term for the s and another term for the s squared plus 1. And since this has a second order or second power on it, the numerator has to be linear, so bs plus c. All right, so with that in mind, we can do the next step, which is to multiply by s times s squared plus 1. So we get this over here, and then on the right-hand side, we get a times s squared plus 1 plus bs plus c times s. Now, we could do what we always do, picking values of s to plug in carefully. It turns out with this one, that's going to be more trouble than it's worth for a couple reasons. Number one, there aren't a lot of values of s that will simplify nicely. 0, for instance, is 1, but after that, you kind of get stuck. And then also with these exponentials, we'd likely end up with non-round numbers, and things would get messy very quickly. So we're going to do it the other way instead, where we multiply everything out and then line up the value, the multiples of s squared, or the coefficients of s squared and s and so on. So on the right hand side here we'd have as squared plus a plus bs squared plus cs. And then on the left hand side we still have the same thing. Now what this means is everything that's multiplied by s squared on the left side is just 1. Everything that's multiplied by s squared on the right hand side is a and b. So that means that a plus b has to equal 1. And then everything else, well, before we go on, everything that's multiplied by s on the right side is c, and there's nothing multiplied by s on the left side. So that means that c has to equal 0, which is nice. It drops off. And then everything else over here has to be equal to this a, because that's not multiplied by any power of s. So a isn't a constant in this case, but it's the same idea, that it still equals everything that's not multiplied by any power of s. So a equals this, and once we know that, b is 1 minus s, or 1 minus a rather, so 1 minus e to the negative 2s plus e to the negative 4s. Alright, so we have our coefficients a, b, and c, which means that y equals, remember it was a over s, so I'll write it this way, 1 over s times a, and then plus bs plus c. Now since c is 0, it's just bs, so that would be, let's do it this way. B is 1 minus all this times s over s squared plus 1. Now to simplify this, let's break these up into smaller pieces. So y equals e to the negative 2s over s minus e to the negative 4s over s. That's the first piece. Then the second piece, we have 1 times s over s squared plus 1. And then we have minus e, well, s e to the negative 2s over s squared plus 1. Then plus s e to the negative 4s over s squared plus 1. Now we can again break this down. We know what y is. We can work backwards and find inverse Laplace transforms. And now that we have it set up with one, we can take one piece at a time and tackle these smaller pieces. So let me, just to keep track of this, let me number these, and we'll take them one at a time. So number 1, notice that that one matches exactly the form of u of t minus a, in this case with a equal to 2. So there's nothing that needs to be done there, it just immediately matches the unit step function that starts at 2. The next one is the same except with 4 instead of 2, so that again matches exactly that form. Nothing needs to be done. The next one, if you look carefully, is s over s squared plus b squared, where b is 1, and so that exactly matches cosine of bt, and if b is 1, that's just the cosine of t. So far everything is kind of conveniently working out exactly like ones that we know. Number 4, this one is a little harder to see, but if you look carefully, it's e to the negative as times another piece. And so looking back in the formula sheet, you should notice that that looks like f of t minus a times u of t minus a. That's the one that had the structure of e to the negative as times another transform. And this is where a equals 2 and f of t equals, or f of t minus, well, f of t minus a, that was the remainder was capital F of s. So little f of t would be the inverse Laplace transform of s over s squared plus 1, which we just mentioned was cosine of t. So this looks like the cosine of t minus 2 times the unit step function shifted by 2. So again, that was not quite as straightforward as the others, but by looking carefully and noticing that it looked just like the step function times a similar function, we can work that out. Then the other one is the same exact setup, except with a 4 here instead of a 2. So again, that looks like number 5 has the same structure. It still just looks like e to the negative as times capital F of s. So this would look like cosine of t minus 4 now times the unit step function t minus 4. So putting it all together, y of t equals the first term, u of t minus 2, minus the next one, and then plus number 3, so plus cosine of t, minus number 4, plus number 5. All right, oops. Coming back here, there we go, okay. And we can rewrite this a little bit. You could leave the answer as is, but just to shorten it up a little bit, I'll write the answer this way. The first two pieces, the difference of those unit step functions is just the pulse function from 2 to 4, then plus cosine of t, and then the other ones, we can't really combine. But there we've got the full answer for y of t. So again, relatively complicated, but once you know how to do each piece, as long as you can kind of follow through the whole process and keep track of what you're doing at each stage, you can get to an answer like this. So this one again started with this pulse function as the forcing function, which led to some of the complexity where we had these exponentials in our partial fraction problem, and then we had a bunch of terms we had to invert the Laplace transform on.